Okay, today we are going to talk about reaction mechanisms and catalysts. And we're going to go through the lecture slides, and I've made a few changes to adapt for the fact that we do not have a whiteboard today. So hopefully you'll be able to follow along easily. We'll start out with reaction mechanisms. So we've looked at chemical reactions and talked about their rate, but we've really been talking about the overall rate of the reaction. A reaction mechanism actually breaks down this overall reaction into elementary steps. And so that mechanism is the series of smaller steps that occur so that way we observe an overall reaction. So here for the overall reaction of 2NO2 plus F2 forming 2NO2F, well, we might observe the disappearance of these reactants and the appearance of the product. What's actually happening are two elementary steps. First, our NO2 and F2 are going to form intermediates that will then react in step 2 of the reaction to form the products that we're interested in. And so we'll see that the formation of NO2F will then be the reactant in our second step. And so we won't see it in the products at all. Same with NO2. It forms in our, it will be left over after our first step, and it'll be a reactant again in our second step. But it's something that we're actually starting with here. Will also form for an intermediate F, which will be and used as the reactant in our second step and will not appear in our products. And so our overall reactants end up being the NO2 and the F2, and we'll use this NO2 here as well. And then our overall product will be the NO2F. And these ones I've highlighted blue are our reaction intermediates, things that will form and then be consumed before the end of the reaction. Looking at this overall reaction again, we can think about it in terms of our reaction diagrams as well. And so our very first step is our NO2 plus F2, forming the intermediates NO2F and F, along with some more NO2. And that very first step has its own activation energy, shown right here. And the intermediates then forming our products are all the way down here, are actually going to have its own activation energy too. And so you can see that we're really looking at overcoming this first energy barrier here to form our intermediates, and then our intermediates reacting with one another have a smaller barrier to the transition state to form our products at the end. So we'll actually have two transition states that occur over the course of the overall reaction. Now, each step of the mechanism is an elementary step, and it's kind of like its own reaction in and of itself. It has its own activation energy, as we saw in the previous slide, but it actually also has its own rate law that is associated with it. And then the rate law for our overall reaction is actually something you have to determine experimentally. And it'll depend on which steps are slow, which steps are fast. And it might be a combination of multiple steps. But if we look just at each individual elementary step, we can actually determine its rate law just by looking at the stoichiometry of the reaction, which is very convenient. So if we have something that is just a one-step reaction, a one, I guess we call it molecularity, which is a mouthful. But if we just have one reactant, so we just have A decomposing into products, our rate will be first order with respect to A. Now, the second, we actually have a 2 coefficient, so this could also be written as 2A. Then we're going to have a rate law that is second order with respect to A. And so really, it's the coefficient that is the exponent on our reaction. And I'm going to take a quick pause. Sorry for the pause. So, as I was saying, the coefficient is going to match our order with respect to a reactant when we're looking at an elementary step. And so you can see here we have now a situation we have two reactants, A and B. And so, since we just have a coefficient of 1 in front of each, then we're going to actually have a first order um, dependence on each A and B. Now, some rare circumstances are when you actually have um, three reactants. So here we would have 3A, and you can see we're third order with respect to A in our rate law. And the reason these are rare is because we're talking about particles actually colliding with one another. And so to get three things to collide in the right orientation with enough energy is even less likely than getting two things to collide with the right amount of energy and in the right orientation. So here's another example of three things now introducing two reactants where we have 2A plus B, and that 2 coefficient will be seen as the order with respect to A. And for B, it'll still be first order because we only have a coefficient of 1 in front of it. And then our example where we have three separate reactants and we'll have a first order dependence on each one of them. So let's look again at our reaction of NO2 and F2 and look at the elementary steps of the mechanism and write out the rate law for it. So looking at our first one, our step one, our rate law is going to be equal to whatever our rate law constant is for this first step. And I like to put a subscript 1 here to differentiate the the rate law constant for step 1 versus step 2. And then we have NO2, one of our reactants. And since I have a coefficient of 2, it will be second order with respect to NO2. And then I have F2. And since I have a coefficient of 1, I'll have first order dependence on F2. And that's the rate law for this first step. For the second step, my rate will be equal to my rate law constant for step 2. And then my reactants are going to be NO2F, NO2, and F. And so it's going to be first order with respect to each of these because my coefficient is 1 in front of each of these reactants. And you'll notice that 2 of these are actually intermediates in my reaction. And we'll talk about this in a little bit, but our overall rate laws are going to need to be based on things that we can observe disappearing or appearing. And so intermediates will not work for our overall rate laws. We'll still be able to describe the rate of this elementary step with respect to the intermediates that act as the reactants, because we're focusing on this as a reaction that stands alone when we're writing these rate laws for elementary steps based on their coefficients. Okay. So another component I want to introduce here is the idea of confirming a proposed mechanism and stating that it's reasonable. When we have an overall reaction, we usually know what we start with and the products that form. And we are often proposing a mechanism rather than knowing what it is. And so if I was studying an overall reaction, I might propose several mechanisms. This would be the more creative side of kinetic studies, where you come up with all of the different ways you think these molecules could collide to form your products. And then you can measure the rate of the reaction as you change concentration. And then you'll be able to decide if your proposed mechanism was reasonable, or which of your many proposed mechanisms is the closest to what you're observing. So we will write out rate laws for each elementary step like we just did often, and then we will also want to confirm that a mechanism is reasonable overall by making sure that those rate laws for the elementary steps would match an observed rate law for an overall reaction that we saw in the lab. And one of the first steps to confirming a mechanism as reasonable is making sure that our mechanism, each elementary step actually adds up to a net reaction that is the overall reaction. And the way we would double check this is just by taking our proposed elementary steps and adding them up. And so I'm going to write all of my reactants on one side and all of my products on the other. So I'd have NO2 plus NO2 plus NO3 plus CO for my reactants, and then NO3 plus NO plus NO2 plus CO2 for my products. Now I can go through and cancel out anything that is both on the reactant side and on the product side. So looking at this right away, I noticed that NO3 on my product side and the NO3 on my reactant side can cancel out. This means this was an intermediate. And that makes sense because our NO3 was formed in our first step and it was consumed in our second step, and we didn't have any left over in our product. Another one that I see that I can cancel out is one of my NO2s. I will use two of these in my reactants and form one in my product. So essentially those will cancel out as well. And then that's going to leave me on my reactant side with an NO2 and a CO, and then an NO and a CO2 on my product side. And I can rewrite this, getting rid of the things I have crossed off, as NO2 plus CO, forming NO plus CO2. And then check this against my overall reaction, which, yep, is NO2 plus CO going to NO plus CO2. So the proposed mechanism will give me the same net reaction as my overall, and that is going to confirm that the proposed mechanism is reasonable in terms of the steps adding up. And now we can get a little bit more practice with writing rate laws for each elementary step. So looking at our overall rate laws for each one, change color. Let's do step 1 first. Here's step 1, here's step 2. For step 1, we're going to write out our rate will be equal to our rate law constant for step 1. And then I'm going to make sure that I'm only using my reactants in my rate law rather than my products. So I've got NO2, and I've actually got 2 of these, right? They're the same, so it's going to be second order with respect to NO2. Now, my second step rate will be equal to my rate law constant for step 2, and then my reactants are NO3, and I have a coefficient of 1, and I only have 1 of these on my reactant side, and then CO. And that's it. So it'll be first order with respect to NO3 and first order with respect to CO. All right. So the next step that we're going to look at in evaluating mechanisms is taking these elementary step rate laws and combining them into an overall rate law. And we don't combine every single step and say that our rate is dependent on some mesh of them all. Rather, we're going to try to determine what the slowest step of the mechanism is, because this will be our rate determining step. The reaction will only go as fast as the slowest step. And there's a great demonstration of this concept that utilizes funnels and with different width of the spouts for them. And that if you have one step that is narrower, a narrower spout, so a slower step, no matter which step it is, whether it's the first step, second step, or third step of a mechanism, it's the one that's going to determine how quickly you see your products actually form. So you can follow this link to a YouTube video put out by Fisher Scientific, that will show a demonstration of this. And it's just a 3-minute video. So take a look at it. Actually, we can pull it up here, I believe, too. We will. Here we go. So we can watch this. This is pretty quiet, so I'm going to move ahead, and you can follow this link on your own and watch the video. But I'm going to skip to where I think it gets interesting, which is when she pours a substance through a set of funnels. And you can see that our first funnel is wider than in the mouth right here. And so it just pours right through it really quickly. And then the second funnel is going to build up a little bit of this substance. But the third funnel is rarely where that happens because it has a narrower opening that you can see right there. And so no matter what, we're going to see that the third step is going to determine the rate of the material going through the funnels into the beaker at the bottom, because it has the, it's kind of like the bottleneck of this reaction. Oh, okay. Sorry. We will pause. All right, if you get an opportunity, I would take a look at that video in full. It's just a few minutes. All right. So let's go back to that reaction we started looking at in the very beginning, NO2 and F2, forming 2NO2F. And we have this reaction diagram we looked at before with two different activation energies for our two steps. We have a first step activation energy and a second step activation energy. And the question is, which step will be the rate determining step? Our first step has a rather large barrier in energy to form the transition state compared to our second step. And so it's actually this really large activation energy that prevents more of our collisions from actually forming our transition state compared to the second step. So this large activation energy step will be our slow step. So in this case, our first step is the slow step of the reaction. Now, earlier we had looked at each of the rate laws for the elementary steps. And so if our first step is slow and our second step is fast, our rate determining step is this first one. And that means that the rate law that we observe, the rate of the reaction that we observe, will be dependent on that first step. And that means we will expect our overall rate law to match the rate law of the first step. So we could say our overall rate law will probably be rate will be equal to our activation, or sorry, our rate law constant times the concentration of our NO2 squared. It'll have a second order rate dependence because of that coefficient 2, and then a first order dependence on F2. So we expect this to be the overall rate law. And this is just because our slow step is first. Okay. When we are evaluating a mechanism and we want to validate it, we won't be able to, this won't be proving it exactly. That's something that has to happen in the lab. But to validate a mechanism, we're going to want to first show that our elementary steps sum up to the overall reaction, like we did earlier. And we're going to want to make sure that the rate law that's predicted by the mechanism is consistent with something that we observe experimentally. And so we'll be able to compare the experimental rate law with the one that we predict based on our mechanism's elementary steps. So we can walk through one of these. Skip a page. Nope, did not skip a page. Okay, so let's look at another one of these. We're going to look at decomposition of hydrogen peroxide to oxygen, which will look like H2O2 decomposing to water and oxygen. I'm going to put a 2 here, and I think a 2 here. 4. Perfect. That's balanced. Yay. So here's our overall reaction. And we have already looked at adding these up to make sure they match up to our overall reaction. Let's focus on figuring out what our expected rate law is. So I have information about which is a slow step and which is a fast step in this mechanism. And the slow step is going to be my rate determining step. And this is what I'm going to build my rate law from. So my rate law is going to be equal to the rate law constant for that first step times the concentration of H2O2. And then I'll multiply that by the concentration of I minus. You'll note within this reaction, we have our reactant and our products. We also have intermediates that form and that disappear. And we also have something a little different. This I minus, it's at the beginning of my reaction. It's at the end of my reaction. One way that I could actually write that in my overall reaction up here is plus I minus and plus I minus. And we'll talk about this in our next topic in today's lecture, which is that I minus is actually a catalyst because it's present both at the beginning and the end. It isn't consumed, it's reformed. All right, but we have for our first step, our slow step, our overall rate law is going to just be dependent on that first step right here. So for those following along, here is what we just came up with. With the slow step as the first step, things are usually a little bit simpler. So now let's look at something a little bit more complicated when, when we have our first step is actually fast and our slow step is second. So in the reaction where we see ozone decompose without a catalyst, we see that 2 O3 molecules, which are ozone molecules, will decompose into 3 oxygen molecules, or O2. So here's our proposed mechanism. We can confirm that this adds up. There we go. Sorry, a little delay on the screen. That this adds up to our overall reaction. If I add up just my products, I'd have O3 plus O plus O3, forming O2 plus O plus 2O2. Again, I'm just, taking all of my products and adding them up on one side of my arrow and all my reactants on the other. And then I can cancel out anything that I see on both sides, and that's my O on its own. And so my overall is going to be O3, and I've got 2 of them, 1, 2, forming 1 plus 2, 3, O2. So great. At least that matches up. Now I'm going to try to figure out what my rate law is actually going to be. So for this reaction, we have an observed rate law that looks like this, which looks a little complicated. And we have our rate law for our elementary slow step is going to be equal to K, our rate law constant, times the concentration of oxygen, the single atom, times the concentration of O3. Now, O3 is a reactant in my overall reaction, but O is an intermediate. And I cannot have a reaction mechanism, or sorry, a rate law that uses the concentration of an intermediate in the law. It has to be based just on things I can observe disappearing and appearing. So let's see how we deal with this. Okay, so here's that rate law we just developed on the previous slide. And what we're going to need to do is find a way to substitute for our intermediate. And we're going to turn to our first step to help us with that. Now, this is our fast step, so it'll be happening really fast. This is also a reaction that is at equilibrium, which I know is our next chapter. But we've already been introduced to dynamic equilibrium. And so at equilibrium for a chemical reaction, the forward reaction rate will be equal to the reverse reaction rate. So it's a reversible reaction. O3 is forming O2 plus O, but O plus O2 is also colliding and forming O3. And at equilibrium, the rates are the same. The concentrations will not be the same of all of our reactants, but the rate of the reactions will be the same. So because of that, we can make a rate law for the forward reaction right here. So the rate of the forward reaction is going to be equal to Kf times O3, because we have just the reactant O3, and we're going to use F for forward reaction and R for reverse reaction as the subscript to our constant. Now the reverse reaction right here is going to have be equal to the rate law constant for the reverse reaction. And then my reactants are actually my products now, so it's going to be O2 and O, first order with respect to each. So now I have rate laws for the forward and the reverse reaction of this reversible reaction that we have in step one. And when this is at equilibrium, we stated dynamic equilibrium, our rates are going to be equal. So I can say that the rate of my forward reaction is equal to the rate of my reverse reaction, which if I can make that statement, I can then substitute what those are equal to and create this equation where the rate law constant for the forward reaction times the concentration of ozone is going to be equal to the rate law constant for the reverse reaction times oxygen times O, or monoatomic oxygen. Now with this, I can solve for oxygen actually, which is really convenient. So if I rearrange this equation, that's all I'm doing, flexing some of my algebra skills, and I rearrange for the concentration of monoatomic oxygen. Look at something that looks like this, where I've got this O3 divided by O2. Now that I've solved for that intermediate, I'm going to come back up to this rate law for the rate determining step and substitute it in. So now, after doing that, this is going to look a little different. So I'm combining these two together, my rate law and my rate law for my first step. And I'm going to get this big thing right here, where I've got all these different rate law constants multiplied and divided by each other, ozone to the second order, and O2, which will be divided by it, which I can really think of this right here as being the concentration of oxygen to the -1, right? The inverse. Well, we're not going to really distinguish between these different rate constants when we're looking at this experimentally. So really, whatever rate law constant we observe in the lab as we change temperature and see the impact on the rate of the reaction, we can say is equal to this large combination of different rate law constants. So if this right here is K observed, then our observed rate that we are now predicting will be equal to the rate times K observed divided or multiplied by ozone to the second order divided by oxygen. And now our rate law that we predicted matches our observed rate law. And so this validates the mechanism experimentally. Let's do another one of these. This is a 3-step mechanism that is pretty made up. And what we have here is a fast first step, a slow second step, and then a very fast third step. So our rate determining step is that second step. I recommend at this point to pause the video and try to work through this one on yourself and develop an expected rate law for the overall reaction. And then come back and hit play again and see how I walk through it. Okay, so my rate that I expect to observe is going to be equal to my rate law constant for my second step times the concentration of C and B. And that's just going off of the fact that this is an elementary step. Now looking at this, where are my intermediates? Well, C is an intermediate. So that means that I need to figure out a way to substitute for C. B is great. I have B in my reactants on my overall reaction, so I'm fine there. I'm going to go to something in my mechanism that has C in it as well. And that is going to be my first step. My third step doesn't have C in it. So this is, again, at equilibrium. So I know that at equilibrium, the rate of my forward reaction will be equal to the rate of my reverse reaction. Now, the rate of my forward reaction is going to be equal to my rate law constant. I sometimes do, instead of just F1, F2, to differentiate it between the second or third step if I have multiple steps that are in equilibrium. So my forward constant times A, the concentration of A and the concentration of B, and these are both first order because I just have one A and one B in my reaction. And the rate of my reverse reaction is going to be equal to K, the reverse of the rate law constant for the reverse reaction, times C, or the concentration of C. So now if these are equal to one another, I can set these two equal to one another. So now K1F times the concentration of A times the concentration of B will be equal to that reverse rate law constant times the concentration of C. And now I'm going to try to go ahead and solve for C so I can then plug it into this equation here. So I will divide both sides by my rate law constant of the reverse. And now C is equal to my forward rate constant divided by my reverse rate constant, all times the concentration of A times the concentration of B. And now since A and B are both reactants in my overall reaction, and they're not intermediates, I can plug this into my rate law to develop my observed rate law, or expected observed rate law. So plugging this in, my rate is now going to be equal to K2 times the forward of my first step divided by the reverse of my first step times the concentration of A and the concentration of B. And then all of that will be times the concentration of B. Since these are all multiplied together, I can kind of group my K's together, and then I can group my concentrations together and rewrite this as rate is equal to K2 times the forward K, all divided by the reverse K of the first step, times the concentration of A, and then the concentration of B squared. So I'm hoping that what I observe experimentally is the rate would be equal to some K observed with a first order dependence on the concentration of A and a second order dependence on the concentration of B. And then I would go into the lab and I would try to figure that out and compare it to this. And if it matched, if I did observe something with a first order dependence on A and a second order dependence on B, I'd be in a very strong position to say, hey, this is probably the mechanism for this overall reaction. And here is that solution typed out. All right, we are going to pause here and discuss catalysts in the next video.